Okay, in the previous video, we were tackling the integral of the hyperbolic cosecant of x. And we used its basic definition, which eventually got us into this form of the integral, which we realized was the difference of two squares. And so we used partial fractions to split this up into two integrals, and then we did some basic manipulations on those integrals to get these expressions, and it looks like these are all set to integrate. So let's get this finished up then. For this integral, we say let u equal 1 plus e to the minus x, then du will equal e to the minus x, and then we'll have minus dx. But up here we have plus e to the minus x dx, so we'll multiply both sides of this equation by negative 1. We get this. So this integral here is just going to be minus the integral of du over u, which will equal minus the natural log of u, which is this. So this integral here, very straightforward, is this. And for the next integral, obviously we want to do the same thing. If we call this u, then du would be, with this minus sign here, du would be plus e to the minus x dx. So this integral is just simply plus the natural log of 1 minus e to the minus x. And so this here, this should be the hyperbolic cosecant of x. And because these are logarithms here, we can write it like this. The natural log of this divided by this. So we have 1 minus e to the minus x divided by 1 plus e to the minus x, plus an arbitrary constant. And this certainly is a valid answer. The reason, though, that we split this up into two videos, whenever you have these natural log functions, it seems like there's always some manipulations you can do with them. And you see here we have 1 minus e to a power, 1 plus e to a power. We can think of 1 as e to the 0. So you have e to the 0 minus e to the minus x. Now, if we multiply both sides of this by e to the x, then we just have e to the x minus 1. Doesn't do us much good. But if we multiply this by, say, e to the x over 2, then this would give us e to the x over 2, subtract minus x plus x over 2, that's e to the minus x over 2, and that's not the hyperbolic sign, but that is 2 times the hyperbolic sign of x over 2. Now, if we multiply the numerator by this, and of course we have to do the same thing in the denominator, so let's just try to do this the right way. This would be equal to the natural, make some room here, this will equal the natural log of 1 minus e to the minus x divided by 1 plus e to the minus x multiplied by e to the x over 2 divided by e to the x over 2 plus an arbitrary constant. Now multiplying across, this will equal the natural log. This will be e to the x over 2. Subtract e to the minus x over 2. And then down here, this would be e to the x over 2 plus e to the minus x over 2 plus an arbitrary constant. And now it looks like this is going to be equal to the natural log up here, e to the x over 2 subtract e to the minus x over 2, 2 times the hyperbolic sign of x over 2 divided by 2 times the hyperbolic cosine of x over 2 plus a constant. So it looks like then for our integral here, the integral of the hyperbolic cosecant of x dx will equal the natural log of the hyperbolic tangent of x over 2 plus an arbitrary constant. And what's interesting about this is we were able now to derive this. It took a little manipulations along the way, but we were able to derive this equation starting with the basic function of the hyperbolic secant, defining it like this. When we tried this approach, though, when we had this problem, and we said that's 2 times the integral of dx over e to the x plus e to the minus x. And we went ahead and worked with this. That gave us a very complicated answer. But when we went and we approached this problem by writing it like this, the hyperbolic secant of x, that is the same thing as the hyperbolic tangent squared of x minus 1. When we rewrote the problem like this, we got an answer right away, no problem. With here, with the hyperbolic cosecant, we put it in its basic definition, eventually we got the answer. But what happens now then if here we rewrite this using, let's see, the hyperbolic cosecant squared of x, that is equal to the hyperbolic cotangent squared of x minus 1. So if we rewrite our original integral like this, and work with it in this form, will we get to this answer much quicker than what we did using its basic definition. So let's check that out in the next video. We're going to use this approach here then, and instead of writing the integral in this form, and see what kind of an answer we can get from that.